Okay, today we'll talk about, we'll continue talking about where we were left in the previous lecture. So last time I made like a very thorough introduction into the CLIP approach. Now we will investigate more into the representations of different pre-training models and objectives, but let's start from where we were left off from last time. So we had this idea of not needing all the time to train ahead on top of some pre-trained model with linear probing or fine-tuning the whole model. So now we gather paired data from the web and train a text encoder on top. So can somebody explain a bit how this figure works in a very high level? What do we do? What is the objective here? Okay, so very briefly, we take one text representation. So for each sentence we have a single representation, and then for each image we have a single representation. And then we compute all the similarities in the mini-bats. So this square matrix indicates all these image and text similarities, where text similarities is a single representation for the whole sentence. And then we do nothing different from contrastive learning. So we maximize the similarity between all the diagonal elements, and we consider all the non-diagonal elements in the mini-bats as negatives. So the main advantage of this method is that it enables us to perform zero-shot learning, as we say. We can, given some additional information, which in the case of image classification is just the label names, we can produce on the fly representations from the text encoder. So these are produced on the fly for each image we want to predict its label, even for a single image. That's why in the literature you will find these models as open vocabulary models, because they are trained on these paired data sets of sentences, and they don't have like a limited vocabulary like BERT-based models, for example, where they have like a large but still limited vocabulary, for example 30,000 words to predict during pre-training. The tricky part we've discussed last week was that the user who is trying to predict, for example, in the classification task, needs to design some text prompts, and we can see that you can have like a very significant performance boost by tuning the text prompts of the CLIP model instead of naively providing the class label. So for example, for satellite images, it's better to provide a description such as a satellite image of, or for a flower-based dataset, a description that is like a flower with a label and then label ID or label name would be much more informative for the model, and you can see even an average performance boost of 5% without actually fine-tuning or training any classifier on top. So these are all really nice, but we want to know what is the main contributing factor to the success, and both in terms of success as well as in terms of robustness towards natural distribution shifts. So we saw that this model is very good at classifying sketches, and now we are trying to investigate why these representations enables us, like what is the main factor where this originates from. So there is a follow-up work from another group in 2022 where they try to analyze all the different possible factors of success of those models. And so you see in terms of training size, data distribution, language supervision at test time, or the contrastive loss itself. And the bottom line of this large-scale study was that the objective itself is not really important. What is important is that you have a very diverse training distribution. So again, we go back to the data acquisition, curation, and collection, which they did to construct these 400 million pairs. So it doesn't really matter. It doesn't really matter if we train with self-supervised learning or contrastive learning based on CLIP or even supervised learning. And to illustrate this, they create some smaller scale controlled experiments. So first, on the top row, they took all the images from ImageNet, these 1 million images, and they mapped them to their original caption that can be found online. And at the same time, they took the biggest image captioning dataset, which has this acronym YFCC. So this is by definition a dataset for image captioning as a task. And they isolated the label that corresponds to the target. So now we have basically the ImageNet in terms of a single class name as well as the description, and the same for the largest image captioning dataset, which consists of 14 million paired data. And again, they saw that language supervision is not the reason of robustness. How do they do that? So they provide this informative plot. Again, how we quantify robustness against natural distribution shifts. We take different ImageNet altered subsets of ImageNet, like these cartoons that I showed last time, or these natural corruptions, or these what else? Or these different types of rendering or sketches. So these are on the y-axis the 4 different natural distributed subsets of ImageNet. So they have the same classes, but the data distribution is significantly different. And the green dots correspond to the ImageNet captions. So training on predicting not just the label with supervised learning, but as an image captioning approach. And the dotted line is the ideal performance that we never get even with the best CLIP model. Nonetheless, they showed that if you look at both these two approaches, so they train this 14 million dataset either with a CLIP objective as well as purely SimCLR naive contrastive learning, plus some classification on top. So this is what the table is showing you. And they show that it doesn't really make a difference. So it's not a matter of the objective, and it's because of the data. Any questions here? So again, the most important part is that the green dots are similar to the blue dots. So this is like supervised contrastive learning, as we typically do, and this is image captioning based training with CLIP. So you see they both follow the same trend on the x and y axis, and then the pink squares as well as the yellow ones also follow the same trend. So it doesn't really matter which objective you use, or if you use the class names or the whole captions and train with CLIP. Any questions? Okay, now we saw that CLIP based, like language image pre-training, is heavily impacted from large data sets. We want to see what's happening in the large data and model scale. So if we could somehow go to larger models, which are really likely to have better zero-shot ImageNet classification performance, what would happen? So these are the different CLIP vision transformers. So this is the last one that they trained. The large, these dotted lines indicate just some fine-tuning for very few epochs on larger image dimensions, so 336. Just in the last epoch was trained with 336 image sizes. And we want to see how much can you scale up. So effectively, we want to emphasize a lot on the connection between representation learning, whether it's language or vision or audio, and scaling. So how much can we keep on improving the models by scaling up the data sets and the models? So even more recently, there is a new work that considered an open source version following the training principles of CLIP, but an open source version of the data that's called Lion, which was produced in a slightly different way. So they used one pre-trained model and they filtered images based on similarity. And they even create another subset of 2 billion image and text descriptions in English. And they said, okay, now we have these two very large and diverse data sets scraped from the web, and let's see what's going to happen, how big models can we train. And what they found out was first that the data set that is used on the study of the CLIP paper, it has this acronym WIT, is more strongly correlated to ImageNet because of the way that it's generated. So last time I said how they collected queries from Wikipedia and then they found images that have this type of texts online, while this data set was produced based on nearest neighbor similarity from a pre-trained model. So the data acquisition and curation already impacts the different downstream tasks. So they argue that this one is more suitable for retrieval-based tasks, while this one is more suited for image classification. But let's see what's happening in different models and scales. So the acronym OpenCLIP means open datasets and open weights. But it's more or less the same contrastive learning objective with image and language as two modalities. So on the x-axis, we see the computational complexity. They don't use flops, floating operations per second. They use another metric that's called MAC. I forgot the acronym. I think it's mean aggregations something. And instead of just, and on the y-axis, we have the ImageNet error. So by error, we mean 1 minus the accuracy. So it's kind of the same, like accuracy. And they try to, so these plots are both on log scale, both on the y-axis, even though it's not really easy to see, and as well as the x-axis. And they try to see if you scale up on compute and models, so larger models and larger computing power, if you can have like if you have like a linear trend, at least on the log scale, in terms of the zero-shot performance on ImageNet. So this type of predictions or trends, discovering these trends, is called in the literature as power laws, what I write here. So given C being the compute, which is the complexity for one image multiplied by the images that are seen from the model, if we can have some estimation of the total zero-shot error on ImageNet. So this is called power law, and we always visualize the log part, because if you take the log on both sides here, take log of E. So beta and alpha are two constants. You can also see them in the plot there. They found the values. So if you take the log on both sides, you end up with alpha and then log and then you can, this is just a constant, so you can treat it as and then you can fit a linear line, like a linear line based on the data points, but on the, is there a question?
Can you say again what the compute was on the C?
The compute is, they take into account both the computational complexity to process one image and multiply it by the images that the model sees through time. So this is something equivalent to the training epochs, is that on really large data sets, the notion of epochs starts to make sense for both practical reasons and so if you have 400 billion data, for 400 million data, the notion of epoch is not really applied. You can still do it, but they do, in practice we just sample randomly each mini batch, and they provide some control experiments to show that it doesn't really make a difference, because it's like a huge collection of images, so random sample is the same as, from the whole data set is the same as epoch-based training. So how many samples the model sees is more or less how much we train the model, and this is how much compute we need to train the model. But do you all see the linear trend that is visualized here? So if we fit the linear lines here, we have these constants, which are these two A and delta that I have shown here. So we always use the log plots to visualize these trends, because it's easier to see the linear behaviors. And I would like to point out the difference between the two colors, so the blue and purple lines, which look something like this, more or less. So this is OpenCLIP trained on Lion, and this is CLIP from OpenAI trained on this WIT 400 million data. So which behavior is more desirable? So in terms of the slope of this line, what we would desire, like what would we want the model? Do we want to have like a flat behavior. They are, let's say, both are linear. Like, which behavior would be desired more in terms of the slope? Yes?
CLIP one, steeper one.
Yes. We want the steeper one because it indicates that we need less compute, so less computational complexity times sample seen. So by training more, the loss goes down much faster in general with the steepest. And this is where they point out the differences. So on the left we have the image error, and on the right we have this robustness cartoons and everything from ImageNet based the naturally distributed subsets. So the main gist here is that the dataset that was produced with from OpenAI has like a steeper curve because of the way it's generated. But still, even with the open source, you can get like even larger models and train them for more. And the other difference is that this coefficient, which indicates the curve, the slope of the curve, is more predictable for the robustness studies. So 0.11 is much closer to 0.13. So we can easily argue about the robustness solely from the ImageNet error on natural distributed versions of this data. Any questions so far? We will see a lot of log plots today. So this is typically referred in the literature as scaling laws. And this is just the table version of it, which enables us to identify. So here we scale up the model. It's indicated with a different. So this is the size of the dots are not really easy to distinguish on the projector, but it's when we see more samples. And then we have different marks for different datasets. So because this is really hard to see, I want to identify some very key nodes based on the table version of this one. So given the smallest vision transformer, the bit base 32, we can already see by going in the small version of the dataset. So we take a subset of 80 million images, and then by going column-wise, so we start with 3 billion samples seen by the model, and then we basically train for more and more and more. And you can see that from 13 billion samples to 34, you already see the bottleneck. So the performance saturates. Why? Because the model doesn't have the learning capacity, as we say, to give us better performance, even though we scale up the compute in terms of seeing more samples. So the main conclusion in these scaling laws and studies is that there are some key parameters that need to be scaled up in tandem, so simultaneously. And if we scan the rows, you can see that going, even with the same iterations, going from 400 million samples to 2 billion samples also gives you a saturation in terms of performance. And you can already see this even with a large version of the vision transformer, which has more than 100 million parameters, trainable parameters. So here you can see that there is this bottleneck. And a very important point is that using these scaling laws, since we fit this line on the log-log scale, we can make predictions. So this is usually called extrapolation. And can somebody imagine why this extrapolation, like predicting how the model, how a bigger model with more compute will perform? Can you imagine why this would be helpful in practice? Why can I, like, why the a priori prediction of the performance of the larger model with more compute would, why would that help me? Yes?
Maybe because it's very expensive to train or to run these models, so if you don't know if they're going to improve, then it'd be a waste of time.
Yes. Yeah, so basically, the more we scale up, the more the training costs. So if these experiments, let's say if this first experiment if the first row costs a couple of hundreds of dollars, this could be on the scale of $100,000. So you can already imagine, both from the exercise classes and stuff, how many times we need to tune all these hyperparameters and everything. So iterating on the scale of, so this model has more than 1 billion parameters. So iterating on this scale with so much compute and so many parameters becomes really infeasible, like intractable even for very large corporations. So that's why we can do these couple of experiments and predict some behavior of the model on the large scale, and then do only one experiment. So this saves us a lot of compute power, which translates to saving costs. Yes?
But this saturation behavior doesn't show up in the curve, like you cannot expect.
Yes, so the linear trend is when you scale up everything. So this is like a more informative version of all the different experiments. So you can imagine if this would be the first point, the next point, so 3 billion samples with the small model. Okay, let's take this one. So from 57.55, you scale up both the sample C and the model. So you, from 57.55, you go here. So these are like the 2 points that you measure. This is like a more thorough version of the plot. They are not exactly equivalent, that's right. So the bottlenecks appear when you scale all but one, when you fix one dimension of scale. And yes, you can see many bottleneck effects that I have identified with these red squares. So how to predict? We do the so-called extrapolation for different models, so bit Z, bit A's, and different types of sample C. And then we can decide to launch those experiments. And does anybody know what is the limit of this? Can somebody imagine what would be the limit of extrapolating? Like, what is the extent of extrapolation? Like, how much can we predict in the curve? There is a small limitation. So the idea is that we want to extrapolate and use this line to predict relatively, the closer that we are to the existing models, the more accurate this extrapolation is, because it's still a prediction. It's not like these power laws will be scaled down in larger ranges. So this would be, I can imagine that this would be the most accurate prediction, and this would be the least accurate prediction. So keep that in mind. Yes? You in the back first.
I couldn't get what is this increase in relation to the upper boundary of this extrapolation.
Can you repeat that?
I don't get this accuracy relation with the upper boundary extrapolation.
Extrapolation?
Extrapolation, yeah. Because you said, according to you said, it's a multidimensional with the scaling factors, right? So you can scale the number of samples, you can scale the model and make some other things. So
Yeah, so here we scale up the model.
yeah.
We use this VZ. So we want to predict this point. So we choose the number of samples. We compute this Z max, the computational model complexity. Then we multiply with the numbers of samples we want to train the model, so how much we want to train the model. And then we could predict this point. So this would be, yeah, okay, this is for 34 billion samples seen from the model. And then we can predict how better the model will perform in terms of the ImageNet or the ImageNet robustness subsets.
Okay, you're saying this when you scale higher, the increase of the accuracy is diminishing, right?
No, if you scale up in this log pod, it follows the linear. So the error goes down, the error is 1 minus accuracy, so accuracy goes up.
Okay, 1 minus accuracy.
Yes, so error is 1 minus accuracy. They just reverse the plot, you can make the same plot with 1 minus the y-axis.
So y-axis.
Yes. What about the other question?
I guess it's similar. So once you have this extrapolation, like, do they usually then try and train the biggest model they can, or is there, how do they decide like how far to extrapolate at what stage? Because like you say, the further you extrapolate, the less confident you are that you're going to be right.
Yes, so it's kind of a trade-off where you have to weigh how much compute you have, how much you can train the model, how much this will cost you, and then you decide on a prediction that is confident enough and it also fits your resource requirements. So it's a really, there are a lot of trade-offs here to be made and a lot of design choices. So that's why I want to emphasize on the intuition of those models, even though you may not work after attending this course in these scales necessarily. You can still apply something similar in a smaller scale. So in a real-life application, let's say you're somewhere in the beginning of the of those data points, and then you want to, you have like, in a real world example, you are allocated a maximum data set, a maximum cost for your experiments from your corporation, and then you have to be very considerate and careful and knowledgeable about how much you can experiment. Any other question? Okay, and I just want to quickly say that there is a strong connection to natural language processing on these scaling laws. So a similar behavior can be seen in natural language by controlling these 3 parameters. So dataset size, number of parameters, and compute. And long story short, you have a similar power law giving you, in the log scale, giving you this this behavior on the test loss. Another consistent finding from vision and language is that, so here it's a bit different scales, token process, so the more we train the model, basically it's just that we count the token that the model is processing, not the numbers of images that it sees. And the y-axis is just the test loss cross entropy, how much you can predict words. And the color indicates, the more yellowish the color, the more parameters the model has. And this is really counterintuitive to what it was believed in the literature, in the scientific community the last 10 years. So everybody believed that a smaller model is more efficient because it's easier to train. But in fact, the last years we found out that larger models tend to be more sample efficient, as we say. So if you follow the more yellow line, which is the bigger model compared to the blue line, so the x-axis is what happens during training. So the yellow, the larger models tend to learn faster, so they need less samples to get a lower test error, even from the beginning, more or less, of training. So this is another finding, both consistent in natural language and vision. And then you can see similar bottlenecks. So you have diminishing returns by deviating from this yellow curve when you reduce the number of samples on your dataset. And here you have diminishing returns by using smaller models. So, long story short, the CLIP-based scaling laws that I presented are quite consistent, like in line with the corresponding findings from natural language processing and pre-training these large-scale transformer models. Just a small note, in natural language we have this generative-based task. So these tasks are more like these GPT-like models, generative pre-training models, which have this decoder which tries to predict, not masking the input, just predicting the next couple of words in the sentence. So let's go back to CLIP. This is a good indication or example that you can kind of play around with this model. You can consider this as sort of break. We're not going to ask you this type of questions. It's just for you to see something that everybody can understand. It feels quite intuitive. So by manipulating, like a human manipulating the image, you can still push the model to make like a very bad prediction and also with very high confidence. So I was a bit curious about this and I want to see if somebody played a bit more with that. So this is just a single blog post showing just one image. So I want to see if other people have experimented with some kind of stuff. And this is the next some sort of game that we're going to play. So you should be able to imagine what the CLIP model will predict on these different scenarios. So we have only two classes, cat and egg. And I will, after you reply, I will tell you the answer for the different setups. Okay, let's start with the first one. Who believes it's let's say egg or cat, whatever. Image number one. Raise your hand if you think that the model classifies the image as egg. Okay, 1, 2, 3, 4, 5, 6. Okay, so the rest, you probably believe that the model classifies the image as a cat. So the answer is, I can't even predict, I'm just letting you know the answer. So the answer is egg with a probability of 88%. Number two, so instead of drawing like the character of the word cat, we now draw a sketch because you remember all these analyses that CLIP is very good to natural distribution sheets and can recognize sketches and all these different cartoons. So, who believes that the model is classifying image number 2 as an egg? Raise your hand. Okay, more people are confident now. The answer is egg. Does anybody want to guess if the probability is higher or lower? Lower? Unlucky, the probability is 93, so it's a bit higher. So this already indicates that the model is more sensitive to characters inside the image than drawings. But this is just playing around with the model. We can't really make like a very, very general conclusion. It's just to help us understand something. Image number 3. Who believes that the model recognizes an egg? Raise your hand. Okay, you are all correct. This is, so this person played a lot with this sticker of the cat, and only when the bottom part of the egg was removed from the image, then the model was able, he fooled basically the model by predicting a cat. You can see the links if you want to see all the different experiments. I just cherry-picked some of them. 62. So let's make it a bit more challenging. I don't know if you can really see from the projector. So this is image number 4. This is like a cat. Okay, the dimension, the size is not very clear maybe in the projector, but we still have to decide. So 4. Who, raise your hand if you think the model classifies this image as an egg? 1, 2, 3, 4, 5. You 5 were correct. So we have egg, and actually with a very high probability of 98% compared to the previous prediction, which means that the model kind of understands this concept of foreground, background to some extent. I'm not making any, it's like more of a fun break. It's not like general stuff, or we will ask you this stuff in the exam. So number 5. So here there is an egg on the back of the picture, but because of the projector and the screenshot, it doesn't look so solid. So who, raise your hand if you think that the model classifies this image as an egg? Okay, everybody correct. So cat with 99% probability. Okay, number 6. This is really tricky. So it's a combination of number 3, just with a cat again next to the side. But you know, you have, as CLIP, you have 2 options. You have to decide in any case. You cannot say. Very hard to say. So raise your hand if you think the model classifies this image as an egg. Egg? 1, 2, 3, 4, 5. You guessed correctly. It still classifies the image as an egg with 80% probability. Again, you can find more samples from this guy online. He has a lot of screenshots and a lot of angles. I just picked some of them. So it's really not clear what does this model learn, what is it sensitive to. It's really hard to guess in advance. But I think you did a pretty good job, at least some of you. Good. So now we're talking about a more like, yes?
Sorry, I just wanted to ask something. You mentioned that it can't say, like, it has to choose cat or egg.
Yeah, because you provide 2 label names all the time, so you have to assign 100% probability to these 2.
Is there any research into models that have like an option to say this is hard, or like an option to be uncertain about?
Yes, this is the probability. You see, for example, in number 3, the probability is much, much lower, so the model finally becomes less confident. But there is no like other quantification, yes?
Can we add a class that says that the model cannot predict or like don't know in this case?
Yes, you can, but it's just that the model hasn't been trained with, like, it always needs to assign the probability. That's a big issue with.
I mean, if you add such a class, will it like cause the model to crash, or what are the
Yes.
costs of adding such a class to?
Probably minimal overhead. It's just that in general, all types of pre-trainings in neural networks are not really good at deciding that this is like not for me. I don't want to decide. This all the literature about overconfident and predictions, because you have to assign this 100% probability one way or another. So the answer to that is the assignment we are seeing from last time. So this anomaly or out of distribution detection. So we want to filter out these images before the model will see them, and it will make like this type of bad predictions. Any other questions? I see you like the game.
C is shocking actually.
Sorry, what?
C speech.
Yeah, there are more examples. You can check it out. So now we are trying to intentionally tune, manipulate the images, but in an algorithmic way. So we take the cross entropy of the test images, and we propagate the gradients in the image space of the validation images on ImageNet, actually in all these datasets, which are indicated with the red. And in the end, you can see we almost reach chance level, okay, slightly above chance level. So this is ImageNet. So the model are like, when you algorithmically manipulate the images, the model has a very hard time, even though this type of distribution shifts are not natural, because it's not like naturally occurring images in the real world, such as this guy playing with the cat and the stickers and everything, or the iPod example. So this is like a very open question in the scientific community, whether this type of attacks, they're called adversarial attacks, so manipulating the images to fool the network by, instead of minimizing cross entropy, to maximize cross entropy.